surrounded by sensors. They're in our cars, our phones, our streets, and even in our homes. But there's one type of sensor that literally sees the world in 3 dimensions: LiDAR, a technology capable of measuring distances with millimetric precision, recreating the environment as a cloud of luminous points. From outer space to interior design, LiDAR is transforming the way we perceive the space around us. Big House Tech will show how it works, where it's applied, the main products available on the market, and what to consider when choosing the right sensor for each project. The light-emitting diode, or LED, is a semiconductor component that converts electrical energy directly into light, efficiently and cleanly. It's made up of 2 layers of different materials, one with an excess of electrons and another with a shortage of them. In simple terms, when electric current flows through this junction, electrons combine with holes and release energy in the form of photons. Unlike regular bulbs, LEDs don't rely on filaments or incandescent gases. Their light comes from a purely electronic phenomenon, which explains their long lifespan and low power consumption. From that same principle, we get the laser, but with a much higher level of control and precision. In a laser, the semiconductor material is placed between microscopic mirrors that make the light reflect thousands of times, aligning its photons in phase and direction. This synchronization creates an intense, coherent, and extremely narrow beam, with unique properties of focus and range. The word laser stands for light amplification by stimulated emission of radiation, a name that perfectly describes this controlled multiplication of photons. When this beam is optimized for measurement and sensing applications, we get LiDAR, short for light detection and ranging. In a LiDAR system, laser pulses are emitted at high speed, travel through space, bounce off objects, and return to the sensor. By measuring the time each pulse takes to come back, the system calculates distances with millimetric accuracy. A rotating mirror allows the beam to sweep the surroundings in every direction, generating a 3-dimensional cloud of points representing everything that was captured. Once processed by advanced software, these data are converted into detailed 3D models, revealing terrain, buildings, vegetation, and even real-time motion. Each point corresponds to an actual measurement, which makes LiDAR essential in autonomous vehicles, geographic mapping, archaeology, and engineering. What begins as a simple light-emitting diode ultimately becomes one of the most precise technologies ever developed to see the world. Not with our eyes, but with light. There are several types of LiDAR, each designed for a specific purpose. Next, we'll classify them by application, grouping them into 7 categories that we'll explore in detail. Keep in mind that a single model can often serve multiple functions, fitting into more than one category. We'll use examples from some of the leading manufacturers on the market. Most of them already have representatives in Brazil, or sell internationally to our region.
Nós vamos lançar um projeto para inovação para incentivar o empreendedorismo. Vai
We'll start with airborne LiDAR, used for large-scale mapping projects. These sensors can be mounted on airplanes, helicopters, or unmanned aerial vehicles, UAVs, commonly known as drones. Their main applications include topographic mapping, forest canopy analysis, floodplain and watershed studies, power line inspection, and in Brazil specifically, dam decharacterization in mining operations. Another major range of LiDAR applications lies in the automotive industry. LiDAR is used for real-time 3D perception in ADAS systems, advanced driver assistance, and in fully autonomous vehicles. These sensors must deliver high frame rates, be compact, and withstand vibration and harsh weather conditions. They enable the detection and tracking of both stationary and moving objects, and are responsible for mapping the environment for autonomous navigation. With real-time information, vehicles can detect obstacles, stop when necessary, proceed when it's safe, and follow their programmed routes. In short, they must operate extremely fast, because what they see is exactly what drives the vehicle's intelligence and decision-making. Smart traffic lights are another creative use of LiDAR technology, an excellent solution for smart cities, improving not only rush hour traffic management, but also nighttime driving safety. In Brazil, Loom Robotics has developed a similar solution for industrial environments.
Founded in 2014, Hesai is a global leader in LiDAR technology. Our team of experienced engineers, scientists, and researchers come from world-renowned companies and institutes. With deep technical expertise and a global leading patent portfolio across optics, mechanics, electronics, and software. Through our proprietary LiDAR architecture and automated production lines, we've redefined LiDAR technology from an expensive research device into a scalable, affordable solution, making it a technology truly accessible to all. Driven by the belief that quality is rooted in design, we built Maxwell, the world's first integrated LiDAR R&D and manufacturing center, spanning 52,000 square meters and backed by an investment of $140 million US. Maxwell enables an end-to-end process that fully covers design, development, testing, and production. It also features the world's largest comprehensive LiDAR reliability testing center, capable of conducting over 100 performance and reliability tests. We have also built highly advanced, fully automated production lines with mass production and delivery capabilities, supported by a rigorous quality control system. By leveraging cutting-edge intelligent manufacturing technologies, we've achieved 100% automation across all core processes. This allows us to deliver millions of automotive-grade LiDAR units each year, meeting the strict standards of global OEMs. We offer high-performance, affordable LiDAR solutions for passenger vehicles. LiDAR acts like an invisible airbag, providing reliable, real-time perception for cars in complex scenarios. Hesai is working closely with world's leading automakers to enhance intelligent driving safety and safeguard every journey. Our innovations are not only redefining the future of mobility, they are also revolutionizing the robotics industry. Robotic vehicles such as robotaxis and robotrucks have already entered large-scale deployment, transforming transportation while greatly enhancing safety and efficiency. Our LiDARs are also empowering smart robots like service robots, delivery robots, AGV and AMR robots, lawn mowing robots, and more, bringing more intelligent and more efficient experience to everyday life. We are strong believers in robotics technology and are committed to building a company to empower a robotics future.
For high-precision scanning of one or more static points, typically mounted on a tripod or other fixed structure, the terrestrial static LiDAR, TSL, is the ideal solution. It is commonly used in applications such as building modeling and structural documentation, industrial plant surveys and as-built documentation, historical and cultural heritage preservation, mining and tunnel mapping. These systems provide extremely accurate 3D point clouds, capturing detailed spatial geometry that supports engineering, restoration, and safety projects with millimeter-level precision. Introducing the Trimble TX6 and TX8 3D laser scanners. The highlight is their integrated HDR camera, which works simultaneously with the laser. While the laser measures precise point distances, the camera captures high-resolution images that can be rendered together with the collected data. Both models feature remote control capability, allowing operators to position and adjust the units in strategic or hard-to-reach locations. They perform full 360-degree scans quickly and can be accessed remotely via Wi-Fi network. Trimble is an American company headquartered in Sunnyvale, California, and has become a global reference in the mining and construction industries. It's hard to visit a mining site in Brazil without finding at least one Trimble device in operation. The fourth group in our classification includes LiDAR systems for mapping highways, railways, and urban structures. These sensors are mounted on land vehicles, whether road or rail, and are therefore known as mobile LiDAR. Their main purpose is to generate detailed maps along their travel routes. Unlike the LiDARs used in autonomous driving systems, which must react dynamically and make rapid decisions in real time, mobile LiDARs focus on precision and coverage. They generally offer higher resolutions, meaning a greater density of points. Most models also come equipped with integrated cameras, allowing the captured coordinates to be rendered into realistic visual models. Bathymetric LiDARs are a fascinating technology that combines principles of optics, remote sensing, and geodesy to map underwater environments such as rivers, lakes, coastal areas, and coral reefs. The basic operating principle is the same as any LiDAR. It emits laser pulses toward the surface and measures the time it takes for the light to return in order to calculate distances. The difference is that in this case, the goal is to penetrate the water column to measure the bottom. A bathymetric LiDAR emits two main types of laser pulses. The infrared IR pulse, usually around 1064 nanometers, which reflects off the water surface and is used to determine the exact surface level as a reference. And the green pulse, typically 532 nanometers, which is able to penetrate the water, depending on turbidity and depth. Part of this light reflects off the bottom, and the return signal is used to calculate depth. The system measures the time difference between the surface echo and the bottom echo, obtaining the exact depth at each point. The green light, around 532 nanometers, is preferred because it's the visible wavelength that penetrates clean water most effectively. In turbid waters, however, the range decreases dramatically, from several tens of meters to just a few. And how are these surveys carried out? Usually with airborne platforms, mounted on airplanes, helicopters, or large drones. The LiDAR is paired with an IMU, which records orientation, a GNSS-RTK receiver for precise geolocation coordinates, and an RGB or multispectral camera to complement the mapping. Data acquisition is done by sensors that capture the return of thousands of laser pulses per second. These pulses sweep across the target area as the aircraft follows its flight path, typically a zigzag pattern, where each line forms a parallel swath. Every measured point produces a 3D dataset with X, Y, and Z coordinates, where Z represents depth relative to the water surface. The collected data are then processed by specialized software that identifies the two main echoes, surface and bottom, and calculates depth using the formula. Depth equals C times delta, T divided by 2 times N, where C is the speed of light, delta T is the time difference between the echoes, and N is the refractive index of water, approximately 1.33. are some limitations. As mentioned, in turbid water, muddy or rich in suspended sediments, the green laser beam loses energy rapidly. The maximum depth ranges from 30 to 50 meters, about 100 to 165 feet, in clear water, and less than 3 meters, about 10 feet, in turbid water. Sea and wind conditions also affect the quality of the return signal. The main applications include coastal surveys, erosion monitoring, nautical charting and navigation safety, draft monitoring, hydrological and environmental modeling, mapping of marine habitats and coral reefs, and planning of port or offshore engineering projects. There are LiDAR systems that can be used on bathyscaphs, submarines, and aquatic rovers. They can be adapted for underwater operation, but in practice, sonars are still much more suitable for submersible applications. That's because light undergoes strong attenuation in water, while sound propagates very well. Although sound doesn't offer the same precision as light, it has a much greater range, even at great depths. In the case of submarines and high-end sonar systems, this range can reach up to 4 kilometers, about 2.5 miles. In the sixth group of our classification are the LiDAR systems designed for specialized challenges. These include models used in mining operations to measure ore stockpiles, or in agriculture, for example, to monitor silo storage levels, or to guide harvesting and fertilizing equipment along pre-programmed routes. Speaking of mining, MapTech holds a strong presence in the industry, offering solutions that range from stockpile mapping to complex 3D underground mine surveys. Their tools are complemented by the well-known Vulcan software and the rest of their 3D geological mapping suite. It's hard to find anyone in mining who hasn't heard of these products.
when you get started, you drive a path, a start and stop path, A, B. You can see the green and the red dot. That's my AB line. I drove right along the road, so all my rows are straight with the road. Once you set that, then you follow that. So when I go load pattern, I call that West Road. See, it shows on the quarter, it shows that. Whereas here is, like, those are the end rows, my straight line on that end, and these little end rows down here. So then this line shows up, and I hook to it, and it turns green, start planting. You can see we're planting 19,500 because this is a dryland corner here. And there's a prescription map that once we get to the irrigated, it'll kick the population back up to irrigated population. There it goes. See, now we're 32.5.
Other LiDAR solutions were developed for security and intelligent monitoring, such as those from Quanergy, which specializes in 3D perception systems for perimeter protection, smart infrastructure, and industrial automation. Imagine a critical infrastructure site, such as a power substation, where security is absolutely essential. Traditional security systems often face serious challenges: false alarms, blind spots, and limited visibility, especially under harsh environmental conditions. A powerful solution comes from Quanergy's 3D LiDAR technology, with its advanced perception capabilities. The system continuously creates and maintains a live 3D map of the environment, detecting movement or changes in real time. When integrated with an AI-based object recognition system, it can differentiate between people, animals, and vehicles, and accurately log each event. With algorithms reaching up to 99% accuracy, the system can evaluate potential threats and distinguish them from routine movements, dramatically reducing false alarms. This enables security teams to focus on real threats while filtering out false positives. The 3D data records also allow for precise diagnostics of potential vulnerabilities and threat patterns in real time, helping predict and prevent future security breaches. Possibly the most widely sold LiDARs today are industrial-grade models, as they are low-cost devices produced at scale for a variety of automation and monitoring tasks. These are typically solid-state LiDARs, compact and robust systems that operate with shorter ranges and lower point density compared to high-end mapping sensors. They are widely used in warehouses and industrial plants, integrated into autonomous robots and automated logistics systems. Their affordability and reliability make them a key component in the current wave of industrial digitalization and robotics. Some of these LiDARs are also found in ADAS, Advanced Driver Assistance Systems, particularly in low-speed or close-range applications, such as parking assist and obstacle detection. Beyond industry and mobility, they are gaining relevance in smart city infrastructure, supporting traffic monitoring, pedestrian detection, and urban automation projects.
Olá, salve, inovador. Vai, chegou a hora de viver a experiência do ESX Tecnologia, ideias e conexões em um só lugar. Você está no ESX, inovação sem cabelo ou desviar. Você já tem o app oficial do ESX? Baixe agora para viver a experiência completa do evento. Faça networking com outros participantes, mande perguntas para os palestrantes, monte sua própria programação e muito mais.
Although Curiosity and Perseverance relied mainly on stereo cameras and optical sensors for navigation, NASA has been actively researching and testing the use of LiDAR for future missions. In Earth-based field tests, conducted prior to actual missions, NASA has integrated LiDAR technology into autonomous rover prototypes, developed at facilities such as JPL, Jet Propulsion Laboratory, and the Ames Research Center. In these experiments, LiDAR is used to map the surrounding terrain, detect obstacles, and plan navigation routes, applying the same fundamental principles used in autonomous vehicles here on Earth. These simulations reproduce the challenging conditions of Mars or the Moon, and the results have been highly promising. LiDAR systems are therefore expected to be onboard future missions, including Artemis and Viper, enhancing both autonomy and situational awareness on extraterrestrial surfaces. China has taken the lead in this field, having integrated LiDAR technology into its space missions since 2013. For instance, during the Chang'e 3 mission in 2013, the lunar lander used a LiDAR sensor during descent to measure altitude and detect obstacles on the Moon's surface. This sensor helped the navigation system slow down the descent and select a safe landing area, performing a role similar to NASA's radar system, but with higher spatial resolution. The U-22 rover from the Chang'e 4 mission, which landed on the Moon's far side in 2019, used a compact scanning LiDAR, or laser range sensor, to avoid collisions and map the nearby terrain. This system was part of the rover's autonomous navigation suite, working together with stereo cameras and inertial sensors. China's Mars lander also employed a laser altimeter, LiDAR, as part of its navigation system to ensure controlled descent, precise landing site selection, and a safe touchdown. According to Tang Baoyi, the vast distance between Earth and Mars severely limits communication, which means onboard systems must operate with a high degree of autonomy, relying as little as possible on remote commands that arrive with significant delays. LiDAR plays a crucial role in allowing these spacecraft to map their surroundings in real time and use that data as the basis for autonomous decision-making. Redundancy through the combination of multiple sensing technologies is also essential to ensure reliability. The Zhurong Rover 2 is equipped with LiDAR sensors for obstacle detection and terrain mapping, an essential component enabling autonomous navigation across rugged Martian landscapes without human control. The CNSA, China National Space Administration, and the Institute of Optics and Electronics have been researching compact, low-power LiDAR technologies for lunar and Martian missions. This research has involved collaboration with Hesai, making it no surprise that a Hesai-built LiDAR has already reached the Moon as part of these missions. There are also ongoing studies on orbital LiDAR systems, designed to map terrestrial and planetary topography with high precision, similar to the NASA GEDI and ICESAT projects.
最大的问题就是它距离太远了，通讯链路受限会比较多，往往是需要一次性注入 一段时间内的所有的动作，隔天以后我们才能够收到所有的执行结果的反馈，就是我们必须要提高火星车的这个自主性。另外呢，火星的地表的环境条件要比月球可能要更复杂一些。最直观的一个结果就是我们可以像所谓叫楔形移动，就是像螃蟹一样可以横着走，这是原来月球车所不具备的。
主要进行它所有的工作模式。正常的工作模式我们走一遍，也会制造一些故障的模式，看它在故障的条件下怎么脱困。实际上我们地面实验呢，就相当于一个它最终发射任务之前的一个考场一样。